Let's share this screen. Great. Okay, I hope this works. Okay, today I will be presenting lecture 28, which is on percent composition and empirical formulas. Yes, let's just jump right into it. Okay, percent composition and empirical formulas. Let's see. Many things have percent composition. Some of these things, like mass of cocoa in an entire cup, it doesn't always have to be just atoms. It can be, I don't know, rubber in a golf club, or what percent mass is that? Or I'm not sure what percent of your phone has crystal in it. What percent mass is in it? So some examples I thought of earlier were amount of cocoa mix in hot cocoa. You have amount of chocolate chips in a cookie, or amount of sprinkles on a donut. So the mass of, for the cookie one, the mass of the chocolate chips, what percent composition is that? There is a percent composition. It's not entirely chocolate chips. So percent composition is percent of mass over something, like an element over the total mass of something. A mass, this is the equation that we would use for percent composition. You take the mass of, well, an element, for example, over the mass of a molecule. So if you have water, you want to know the mass of hydrogen inside that water. You take the mass of hydrogen over the total mass of water, times it by 100, and you get your percent composition. Percent composition has to do with mass. That's the important takeaway here. So the cookie example, you take the mass of chocolate chips in a cookie, take their mass in grams, divided by the mass of the entire cookie, the chocolate chips included. So I don't know how much that would be, but you times that number by 100, and that's your percent composition of chocolate chips in a cookie. So let's run an example. Baking soda. Baking soda. How much sodium is actually in baking soda? Baking soda is great for experiments. This sodium is amazing for, it's an amazing, if you mix it with some kind of citric acid or some other acid, then it creates gas and it creates this amazing experiment you can do at home. So how much of the sodium sodium element is actually in baking soda? All right, so first of all, assume there's 1 mole of baking soda, whatever you're doing for your calculation. 2 is find the total mass of 1 mole of baking soda by adding all of the molar masses. So I did not put the chemical formula, but I have it right here. There's going to be I do have the chemical formula right there, whoops. Chemical formula is 1 sodium, 1 hydrogen, 1 carbon, and 3 oxygens. So if we want to find the total mass of all of these, we're just going to add up all of them together, assuming there's just 1 mole. So 1 mole of sodium gives us 23 grams, 1 mole of hydrogen gives us 1 gram, 1 mole of carbon gives us 12 grams, and 3 moles of oxygen and 1 mole of baking soda gives us 48 grams. And you add those all together and you get 84 grams for 1 mole of baking soda. Okay. So now that we have the total mass, we need to find the mass of sodium in 1 mole of baking soda. So luckily for us, there's only 1 mole of sodium in baking soda. It's pretty easy. It's 23 grams of sodium in a mole of baking soda. Now you divide the sodium by total mass to get percent composition. So you divide the mass that you want, the sodium, 23 grams, divided by the whole thing, 84 grams, and you would get, well, first of all, you times by 100 to get the percent. You would get an answer of 27.4% sodium. That is your answer for percent composition of sodium in baking soda. Not too bad, right? Okay, now comes the question, what if we don't know the chemical formula? And I don't know for every case, there's probably other ways to do this, but for hydrocarbons, we can get fancy. We can use what we call combustion. Yes, combustion. So This is how combustion works. It's called combustion analysis. Combustion analysis is the burning of a hydrocarbon so that we can find the carbon, oxygen, and hydrogen components, or whatever else we want to measure if we have something to catch it. And this is the way it works right here. You place the hydrocarbon in there, you weigh it first, and you place it in here. It's combusted with oxygen. And when it's combusted, the stream, it's going this way. It's going towards the CO2 and H2O collectors. And so when combustion happens, hydrocarbon is combusted with oxygen to produce carbon dioxide and water. And so when that happens, the carbon dioxide that's produced is collected. So is the water. And, some of the oxygen is used. It's not part of the hydrocarbon that we put in. And so it's a little tricky, but we can do this. So first of all, when combusted, excess oxygen, hydrocarbon will give off carbon dioxide and water as products. For example, when we combust 0.225 grams of an organic compound, we collect 0.512 grams of carbon dioxide, 0.29 grams of water, has a molar mass of 116. That'll be important later. So we collected these numbers. Even though our organic compound sample was only 0.225 grams, we collected 0.5, so almost double, more than double the weight carbon dioxide. Isn't that interesting? And water we collected almost just as much as almost the same weight as the compound that we put in. So we have 0.209 grams of water, 0.512 grams of carbon dioxide, or 0.225 grams. With the amount of CO2 collected, we can find out how much carbon we have. Same goes for hydrogen and water. This is why hydrocarbons work this way. So there's our carbon right there. We collected 0.512 grams of carbon dioxide. Do a little dimensional analysis. Cancel out those units, and we convert it to carbons, and we get 0.14 grams of carbon. For water, we have 0.209 grams of water. A little dimensional analysis. 18 grams from 1 mole of water. 1 mole of water goes to 2 moles of hydrogen. That's supposed to just be hydrogen, but 1 mole of hydrogen is just 1 gram of hydrogen. You get 0.0232 grams of hydrogen. If we're given the total mass of the hydrocarbon we started with, we can subtract the carbon and the hydrogen we collected to find out the remaining mass, which would be the oxygen in the hydrocarbon chain, because that's the only other element left. So we have 0.225 grams total minus 0.4 grams of carbon minus 0.0232 grams of hydrogen, and we get 0.061 grams of oxygen. Perfect. Okay. Now that we have the masses, we can find the percent composition. So all you gotta do is divide it by the total mass, which we're given, 0.225 grams sample. So 0.14 grams of carbon divided by 0.225 grams total, times by 100, it gives you 16.2%. Hydrogen, 0.0232 grams of hydrogen divided by 0.225 grams total gives you, times 100, gives you 10.3% hydrogen. And for oxygen, 0.0618 grams of oxygen divided by 0.225 grams total times 100 gives you 27.5%. This is our percent composition of our hydrocarbon. Okay, percent composition, finding the empirical formula. Now that we have these percent compositions, we can find the formula. Right, let's hop right into it. Okay, so finding the empirical formula. From the last step, you take the percent composition of elements and write them as grams instead, assuming 100 grams total mass. Okay. So imagine you have 100 grams of this hydrocarbon chain. You know, the percent mass, you're going to have, whatever percent you have, you're just going to have that many grams. So if you have 62.2% grams of carbon, for this example, I'm going to turn this to 62.2% grams. 62.2 grams. Does that make sense? I'm just going to convert it into grams. Next, you need to find the number of moles of each element present. So that shouldn't be too hard. All you got to do is divide it by its molecular weight. If you have 62.2 grams of carbon, you divide it by 12 grams. It's its molecular weight, that's how many moles you're going to get. The grams are going to cancel, and you will just be left with moles. In this case, we have 5.18 moles of carbon, 10.3 moles of hydrogen, and 1.72 moles of oxygen. Great. Now that you know how many moles you have in this, in your sample of 100 grams, you divide each by the smallest number of moles. Divide each. Now that you have that, you divide each by the smallest number of moles. So what would that be here? Oxygen, 1.72 is your smallest there. So if you divide it each by 1.72, it gets really interesting. You know, because molecules aren't going to be halves or quarters. You're not going to have half of an oxygen molecule. You're going to get pretty nice numbers. 100, that's really close. So you have, to divide that, 1 mole, 1.72 moles of oxygen. 1.72 moles, you get 1. If you divide 10.3 moles of hydrogen divided by 1.72, you get 9. The carbon goes to 3.01. Very nice number. Now, if you round to the nearest whole number, usually, you'll get, well, you're usually going to be within 100th to a 10th to the nearest whole number, and so you'd round just to the nearest whole number. If needed, multiply results by 2 to get within a 10th of a whole number. That did not happen here, thank goodness. But if you have, say you had, for the hydrogen, say you only had 4.5. 4.5 is you would just multiply the whole row by 2, getting 2, 9, and 6. And you would have whole numbers for whole molecules of an element. Make sense? So if you bring those together, you get the empirical formula, which is C30H6O001. All right. But the empirical formula does not, I repeat, does not equal the molecular formula. They are different things. Our formula of C3H6O may not be correct. The empirical formula has the lowest possible factor of enough numbers for a molecule. For example, our C3H6O could be C6H12O2, right? All we were given was these basic numbers. Very lowest numbers. We don't know the molecular mass of it unless we don't know the molecular mass of it. So we don't know the molecular formula. All we know is the empirical. Another option could be C9H18O3 or C30H60O10. It just could keep getting bigger. We don't know. But we can figure this out by mass spectrometry. All right, mass spectrometry. I don't know if you can see that picture with my face in the way, but you're going to have a mass spectrometry. This is very interesting. I cannot explain it completely, but if you run it through, it's going to diffract off of one way. It's going to emit a light. You shoot the particle, you shoot the hydrocarbon, it's going to emit a light. And depending on how far that light, you know, goes off from the center, when you put a magnet next to it, you can weigh how heavy it is. If it's heavier, it's not going to go as far. That is heavy. You know, the light's going to go a little bit farther the other way from the center, and that way you can measure the mass of this object, molecular mass. So if you combine this empirical formula that you found, along with this new molecular mass, great. Measure, compare, and you can find the molecular formula. Okay, finding the molecular formula. Let's say that this substance that we combusted had a mass of 136 AMU, as measured in the mass spectrometer. So here's what we do. We divide the mass from the mass spectrometer, say that spectrometer, by the mass from your empirical formula. So let's see. Our mass that we got from our empirical formula, you remember it's C3H6O. So C3 would be 3 times 12, 36. H6 would be adding 6, 42. adding on wrong, isn't it? Huh. I did the math. C3. Dang, yeah, I did the math. That's funny. Did I do it wrong? I did. 36. 42. Let's just go ahead and fix that there. Okay. C3H6O. So 36 plus 16 is going to be 46. 52, 58. It's only going to be 58, not 60. That's my bad. Let's go ahead and edit that real fast. In 2 seconds. Wow, guys, I cannot do math today. Great. Let's try that again. Share my screen one more time. Sorry about this. Okay, so here we have, back to it. Here we have our actual from our molecular formula. We have this C3H6O. So from C3H6O, we get 36 plus 16 gives us 46, 52, plus another 6 from those hydrogens gives us 58. That's all I'm asking. I'm pretty sure you're right. Okay, but let's say that, oh, sorry, this should say 116 as well. I don't mind that. Say that this substance that we combusted had a mass of 116 AMU as measured in the mass spectrometer. Just say 116. Divide the mass from the mass spectrometer by the mass from the empirical formula. Okay, so our empirical formula gave us a mass of 58. The mass spectrometer gave us 116. Give us a multiple of 2. Right? So multiply this number with your empirical formula. And this gives you the molecular formula. This is what we want. So the mass that we measured was double what it is in the empirical formula. So we just double that. And this gives us the final answer of C6H12O2. And that would be our molecular formula, right? Usually the mass that you measure in the mass spectrometer is going to be a nice number that works very well with the empirical formula, because it's not going to sway very far, unless the molecule is very big. It's going to be a very nice multiple. It's usually going to be about double what your empirical formula, the molecular weight from your empirical formula is. And that is the end of slides. That is the end of the percent composition. So in hindsight, percent composition is things like this. And percent composition is mass. Percent mass of something over percent mass of something else. The baking soda example. We have combustion analysis. So if we don't know the formula beforehand, we can figure the formula out through this analysis. We get the empirical formula by collecting these numbers, collecting the amount of carbon dioxide and water. Through that, we can find the percent composition of oxygen, hydrogen, and carbon. From this, we can find that formula. In review, we can take these percents, and we can go convert them to grams. We can find the moles, divided by the smallest number of moles to get the whole numbers, round whole numbers. We can get the numbers. From the mass spectrometer, we can get the 116. From the mass spectrometer, we can get the multiple. In this case, it's 2, and multiply that by the empirical formula. That is it. That is lecture 28. I feel more confident about it going through this. If you have questions, feel free to email me if you want to. Yes. Thank you very much.